All right, so I'm going to do a quick summary of the hormones that affect nephron transport. All right, so I'm going to put those, and again, said this at the end of the last video on nephron, with the nephron summary. Most of these hormones are active at the DCT and the collecting duct, cortical collecting duct. One of them is active all the way down to the bottom of the collecting duct. That's going to be ADH. So what I want to do is sort of put them on specific teams and sort of group them together at least a little bit. And so let's make a list down here at the bottom. I'll try to squeeze this in. All right, so angiotensin 2 is a stimulus for aldosterone and ADH. Right? It's not the only stimulus, but it is a stimulus. And so anytime blood pressure is low, GFR is low, we're going to get the stimulus for renin, which leads to the production of angiotensin. It's actually angiotensin 2. That's the active hormone. And it's going to stimulate these other two hormones. And so logically, the effect here is that if blood pressure is low, it will cause GFR to fall. Right? And if blood pressure is low, we really want urine volume to be low. So what angiotensin 2 is doing at the glomerulus is protecting GFR from the low blood pressure, right? So it's constricting the efferent, which will make GFR stay up toward normal, right? But then we really don't want to lose a large volume, so it stimulates reabsorptive hormones. Now the ADH is pretty simple because it will stimulate, and again, this would be a DCT cell or a collecting duct cell. There's already an aquaporin over here in the basolateral membrane. That one's always there. There's another one that moves in and out of vesicles inside the cytoplasm that responds to ADH binding receptors and stimulating the second messenger system that's going to result in the insertion of vesicle stored. Right? So here's a vesicle. Here's the aquaporin 2 channel. And again, there would be more than one of them in the vesicle. But this vesicle is going to fuse with this apical membrane. And when it does, this whole membrane of the vesicle becomes incorporated into the apical membrane, including the aquaporin 2. And so we end up with, right, AQP2 in the membrane. Well, and again, now as long as we have an osmotic gradient between the tubular fluid and the interstitium, then we now have a full pathway for water reabsorption. Right? And remember, our peritubular capillaries out here would be collecting that extra reabsorbed water. Okay, and in the absence of ADH, these aquaporin 2s are pulled right back out of the membrane, back into vesicles, and then of course we no longer have this transcellular water permeability. More water would stay in the nephron, and urine volume would go up. And again, it's called antidiuretic hormone, right? It's causing us to conserve water. So if we add it, we have the pathway, and we're bringing the water back into the body, into the peritubular capillary blood. In the absence of it, the extra volume will stay in the presence of less. More water will stay inside the nephron and exit in a larger, more dilute urine volume. Okay, note, and I drew a single cell here of our nephron segment, but an important point to make is that our tight junctions are now much tighter, right? Draw an adjacent cell here, or part of it. Right? And the point being that the water cannot move passively, paracellularly, right? So we can actually control the amount of water that we reabsorb here by forcing it to go through the cell in a transcellular pathway. Okay, there's ADH, allowing us to conserve water. Now we have, I'm sorry, I want to add one other thing here. Another key stimulus for ADH is an increase in what I call piosm or plasma osmolarity. All right, and again, it makes sense. If osmolarity of the body, extracellular fluids, is going up, we need to retain more water to dilute it and bring it back down to normal. And so, at the hypothalamus where EDH is actually secreted, we've got osmoreceptors that feed in there, brain osmoreceptors that feed in there, this information about osmolarity. And again, when it's high, we want this pathway. So we're going to add more ADH. We incorporate the aquaporin 2s, conserve more water, and dilute our extracellular fluid volume, right? Okay, now up to aldosterone. Aldosterone allows us to control and regulate sodium and potassium excretion. And so what aldosterone does is it stimulates sodium reabsorption. And it does that through stimulating an increase in sodium potassium pump expression, which is going to put more sodium into again, add our peritubular capillary down here if you'd like. Right? More sodium into our peritubular capillary. That's the original water. Right? We've reabsorbed more sodium. Now, we have to get it across this membrane as well, and so it also tends to enhance specifically channels, ENaC, epithelial Na sodium channel, and so that's going to allow sodium to enter more readily from the apical side, and now we've fully reabsorbed the sodium. It also enhances potassium secretion, and so the potassium that entered the cell is a high potassium in here. All we really need to do is provide more significant potassium permeability here, and now our potassium ends up being secreted to a greater degree. Right? This was sodium coming in. Right? And so there's our actions. We've saved more sodium, we've reabsorbed more, saved more sodium, we've secreted more potassium. So, because sodium is such a dominant electrolyte in the extracellular fluid, right, we're actually going to end up conserving more water with it, and we tend to boost extracellular fluid volume, blood volume, with the increased sodium reabsorption. So if we go back to our original stimulus, at least coming from the angiotensin II, remember that was low blood pressure that stimulated renin. Now we're conserving sodium. Because we conserve more sodium, reabsorbing more, we're going to reabsorb more water, which means our blood volume will go up, which means our venous return will go up, which means our stroke volume will go up, Frank-Starling mechanism, which means our cardiac output will go up, which means our blood pressure will go up. You can never forget the blood pressure plus cardiac output times total peripheral resistance. Right? If we increase cardiac output, we increase our blood pressure, helping us to solve the original problem. Now, aldosterone is also and more potently stimulated by hyperkalemia, which is high potassium levels in the extracellular fluid. And that makes perfect sense. High potassium levels in the ECF are very dangerous because potassium efflux from a lot of cells, movement out of those cells, is very important for repolarization. In neurons, in muscle cells, think heart, right? Super duper important. So we have to avoid having our extracellular potassium become too high, and it would oppose repolarization. That would be catastrophic, right? And so we need to, when those potassium levels become too high, right, initiate our aldosterone secretion, more aldosterone secretion, and enhance our potassium excretion through secretion, right? Okay, those three basically work together to increase blood volume and blood pressure, right? Now we do have a hormone called ANF or ANP, and what ANP or ANF does, a big chunk of its action is actually through inhibition of renin. And so if you think about it, what it's really doing, get back around to here, is just inhibiting this whole system I just explained. And so instead of increasing sodium reabsorption, it's going to decrease it, which is going to decrease water reabsorption, which is going to make our urine volume go up, which makes our blood volume go down, right? And again, decreased blood volume, decreased venous return, decreased EDV, smaller stroke volume, decreased cardiac output. We just reduced our enhanced blood volume and blood pressure, right? The stimulus for ANF is, guess what? High blood volume. It's produced by the heart, the atria of the heart. There's another natriuretic peptide that comes from the ventricles called BNP, a little less potent. ANF is the more dominant one. And it's stimulated by increased distension of the atria. Well, you get increased distension of the atria when you have increased venous return. You get increased venous return when you have an enhanced elevated blood volume. It's called hypervolemia, extra volume, right? Hypervolemia. And so high blood volume stimulates ANF, inhibit the angiotensin II, inhibit reabsorption, right? Excretion would go up, helps us solve our problem, right? You might think, oh, what does ANF do to the glomerulus? Well, we would probably want more GFR, enhanced GFR a little bit. Yes, it's well autoregulated, but if we can bump it up just a hair, right, because it's so big, and then allow excretion of that extra volume, we would also rapidly solve our volume problem, right, with hypervolemia. And so we would, ANF causes afferent dilation, increases glomerular capillary hydrostatic pressure, more filtration, right? Some people say it actually constricts the efferent, although there's some debate about that, but that would also tend to increase glomerular blood hydrostatic pressure, which enhances GFR. Okay? The last two we have to do are, one last thing, is ANF also has direct effects. It can have direct effect on transport of sodium, and again, it's going to go in the direction of decreasing the reabsorption of sodium so that more stays in here when our excretion goes up. Remember, natriuretic means excretion of more sodium in the urine. Right? Kind of sounds like diuretic, but it's got Na in front of it for sodium. Okay, the other two hormones, I'll squeeze them up here, are PTH and calcitriol. So those two hormones work together as a team, and actually PTH stimulates the production of calcitriol. They work together to enhance extracellular calcium levels, right? Making it so, in other words, if you are hypocalcemic, your blood and extracellular fluid calcium levels are too low, we need to retain more calcium at the nephron, reabsorb it, to boost those levels back up. These hormones, PTH specifically, actually acts at bone to do this as well. The calcitriol acts at the GI tract to enhance calcium absorption from our dietary intake. And again, all those working toward boosting extracellular fluid free calcium ions. So, what do? Well, we need to get calcium from here to here, right? Over here we have one of our ATPases, one of our primary active transporters. It's a calcium ATPase. All right, so the question is, how do we get it across the membrane over here? And that's pretty simple. We can just add more, let me make that look like a channel, more of a sodium calcium co-transporter. Right? We're going to use sodium moving down its gradient to drive calcium into the cell. And again, the calcium is probably already low here. And so they may both be going downhill. But if it's not, because again, we're pumping it out on this side while it's entering on this side. And so you can get some kind of crazy calcium concentrations. But the problem here is that calcium tends to stimulate lots of things inside the cell, right? Calcium tends to activate, second messenger systems and all sorts of things that, or play a part in second messenger systems. And so we need to regulate the free calcium inside the cell. We do that, that's what calcitriol comes in. Calcitriol forms what's called calbindin. So the calcium, it's a calcium binding molecule, and the calbindin then keeps the free calcium from being free, essentially, by binding it, and it delivers it to the basolateral membrane where it's pumped out of the cell, and therefore it comes off of the calbindin, and we sort of go in a cycle here where the middle, with calbindin acting as a middleman, transporting calcium across the cell, keeping the intracellular levels low. Okay, and again, I don't want to. We can add other pathways for calcium here. We could actually use a channel because the filtered calcium may still be high enough to enter the cell passively. Right? But PTH tends to stimulate those transporters, whereas calbindin, the calcitriol stimulates calbindin, which binds the intracellular calcium to keep it low, so that it doesn't turn on everything in the cell. And we transport to the other side of the cell and reabsorb it, increasing our extracellular fluid calcium levels, opposing our stimulus here, which I didn't write down, which is hypocalcemia. Right? Stimulus is hypo. We're saving the calcium, reabsorbing it to bring it back up to normal. Okay, got them all.